Last class, we talked about the main hardware components which are needed to design a processor. So we looked into that. We have found that these are the components which are major components which are needed to design a processor. Register file, instruction register, then arithmetic logic unit, instruction address generator, which also includes the program counter, a control unit, and processor memory interface. Okay, now these are the major components. There are other components which we must know, and also we need to know that how these components are actually connected with each other. So that's what basically we will learn now. Gradually we will open up the system. Okay, now so we'll start with CPU designing. Okay, now one component, it's a common component which we need to understand. That's a data processing hardware. So a data processing hardware has various functions inside a processor. Okay. So how do we, so what I'm going to represent is a generic data processing hardware. It may not be exactly matching with each and every component of the processor, but the concept remains the same across all the units, functional units of the processor. So can someone tell me where actually what kind of circuit is needed to process the data? Digital circuit. We are talking about processing data. We are not talking about storing the data.
Something like a mux.
It's not marks. Multiplexer is yeah. So adder is fine. Multiplexer is one type of data processing unit. Yeah, so we can say that a combinational logic circuit. What we can say, a combinational logic circuit is needed to process the data. It can be a multiplexer, it can be adder, subtractor, multiplier, logical and operations. So we can say it's a combinational logic circuit. Combinational logic circuit. Now, what it does basically, it takes some input and it produces some output. So any such combinational logic circuit, you need to define that where from the inputs are coming. That is very important. So can someone tell me what should be there on the left side and what should be there on the right side? Logically, think about it. What should be there in the left side? What should be there on the right side?
Input and output.
Yeah, input output is fine, but where from the inputs will come? Think about. Sorry?
Registers.
Yeah, registers, right. So register. So what we can say that on the left side you have one temporary location. You can say a register. Say A. And what these registers contain inside these registers? What are the circuits? Anyone?
Flip-flop.
Yes. So we have flip-flops. It means inside this we have flip-flops. Now let's, for the sake of simplicity, make it a D flip-flop. What else we require? On the right side also we shall have a same unit like this. So do you agree with me, this one? Now what else needed in this circuit?
Sir, might be we need one more register for input.
That's correct. Say if the combinational circuit performs an operation, we may require multiple inputs. But let's assume that multiple inputs are going through this one itself. When I'm saying register A, it may be register A and B as well. Okay. This is a combinational circuit. These are sequential circuits. Okay. So what you need is basically the clock cycle. And this clock is a global clock which is given here also. So with the help of this clock, we transfer the data from here to here. Since this is a combinational circuit, you can ignore the delay here, delay del, which is, for the time being, we assume that it is 0, though it's not 0, it cannot be 0. Every combinational circuit has its own delay. We shall come those things later stage when we'll design the paths. But for the time being, we can assume that this delay is 0. If this delay is 0, so whenever the input is given, the combinational circuit produces the result. Instantaneously, the result is given to the input to the next flip-flop. So what happens basically? The data comes from here, gets a transformation, and it basically goes here. So what I can write, P is equals to, there is a function and we actually do like this. It may be A comma C also, something like that. And this F is the combinational circuit.
So can you
I'm writing,
clarify C? Oh, okay. Okay.
so is it visible now?
Yes.
So B is the output, which is nothing but a function of A. So this function is combinational circuit. So we can write this is the function which may take multiple inputs. So for the time being, we are just assuming that it does some sort of transformation. Okay. Now this is a generic function And all such units that we have talked about earlier, they actually, perform something like this. And our objective is to implement these functions within a framework like this. Okay, so this is a generic circuit representation of data processing hardware. What can be the combinational logic circuit? It depends what you would like to do. It can be a simple transfer. It can be simple logical operation. It can be simple arithmetic operation. It can be simple control signal generation also. A decoding can be also done here itself. But the data comes, it does something, it produces something, the result goes to another register. Okay. Usually like this. Now outputs can directly be connected to, like when I was talking about, this is a decoding unit. The value comes from instruction register. It goes to the decoding unit. You may not store the value output of this combinational circuit directly into a register. You may directly use it for some other purpose. Okay, so the output side can still change. Okay, because you may require individual signals rather than taking the whole output. Okay, so there I will represent not B, maybe B1, B2, B3, something like that. So that's just basically breaking down the problem into small signals. Now, this is one stage actually. So we have looked into the basic designing that the processor actually works in various stages. So you can assume that this is stage 1 register. This is stage 2 register. So at stage 1, so in between every stage, you have a register that actually stores the data temporarily. So what will be a typical structure, a hardware structure with multiple stages? Look like something like this. So we can now summarize this as a circuit like this. We can have something like this. This is register. This is register. This is register. This is register. And we have logic circuit. This is logic circuit. This is logic circuit. And the values are, or the data is transferred like this. So you apply the clock. This register's value will be processed by this logic circuit. It will be stored into this register. This register's value will be processed by this logic circuit, will be stored into this register. This register's value will be processed by this logic circuit and will be stored in this one. So you can say that now these are your stages. You can say this is your stage 1. This is stage 2. This is stage 3. You can keep on doing this. So it's a typical hardware structure with multiple stages. The circuits will vary. Okay. So now with this concept, we shall try to understand that how the instructions in a typical RISC style instructions like MIPS, how the instructions can be designed using these various stages. Okay, so we shall now take specific instructions and see that what are the requirements for those instructions. That will help us to design the circuit. I told you this is ISA, instruction set architecture. We first design the instruction, then we go for the architecture. It's not like that we initially design the architecture and then see that what the architecture supports. So we are talking about ISA, instruction set architecture. That means our architecture will be based on the set of instructions that are going to be implemented. It's not the reverse one, that you design the architecture and then see that what are the instructions being supported by the architecture. That's not the case. Now why we have finalized the instructions? We have already discussed it, that for any given problem, what are the different types of operations? And we have seen that to complete these operations in a generic way, we need certain types of instructions that we have already looked into it. Now, possibly, we have to decide that how many instructions are there in your design, and let's see that how can we come up with a generic circuit for that. Okay, so a systematic way of deciding that what will be these logic circuits, because you have been given with a set of instructions. Instruction set architecture means a set of instructions. Now you cannot design separate hardware, this multi-stage hardware for each and every instruction. That's not viable at all. Every instruction will be having separate pipeline. It's not possible. So we need to understand the commonality of various stages across various instructions and then try to come up with the hardware solution. So identifying common activities across or inter instructions. It's not inter instruction activities. The activities which are common amongst various instructions, we need to identify them. And then probably we can design a generic circuit so that the same circuit can be used by all instructions. Like you design an adder which can add register R1 and register R2. You do not need to design another adder which will add register R2 and R3. The same adder can be used. Or maybe an immediate value and a register you need to add. Do you think that you will design another adder for that? No. We'll have to use the same adder for adding R1 with R2 as well as R1 with R3 as well as R5 with R6 as well as R30 with R31. So we need to understand that which stages of various instructions are common and what can be a generic circuit for that. Okay. So this leads to a step that we need to examine the actions involved during various stages such as fetching, decoding, and execution of the instructions. So for doing this, we take examples of typical RISC style instructions. Okay, so we shall now take examples of RISC style instructions and let us try to understand that what are the steps. We need to examine the actions involved, actions or steps. Okay, you can write down these actions or steps. Now let us take examples and see that what are those actions needed. Let's take one instruction. Example 1. Let's take load. R1, comma, X, R2. What it does actually, if you look into the description or register transfer notation, let us write the description. So it uses the index addressing mode to load a word of data. It loads a word of data from memory location what is the location? Location will be X plus R2 into the register R1. That's it, what it does. So the steps to execute the instruction. Let us write down the steps to execute this instruction. Tell me one by one, what shall I do first? What should be the what I need to do at the beginning?
Get the instruction.
Yes, get the instruction. So in terms of technical language, we call it fetch the instruction. So fetch the instruction from where?
From memory, from
Yes.
location pointed by program counter.
Right. So fetch the instruction from memory. From memory, location pointed by the program counter. So this is the correct complete statement. Fetch the instruction from the memory location pointed by the program counter. That is the first step. Second step,
Increase the program counter.
yes. So increment the program counter. Because it should point to the next instruction to be fetched. Next stage,
Decode the instructions.
yes. So decode the instruction to determine the operation to be performed. Fourth stage, not stage, I'm not talking about step. I'm talking about steps here. These are not stages. Multiple steps can be included into one stage. What will be the next thing? You understood that what will have to be done by decoding. Then what? As per this instruction, what you'll have to do?
Okay.
Load required data into some register.
Which one?
Load required, like required data as in like if it's addition, then loading the number, or if it's
No,
adding
where is the loading the number? Where is the addition? There is no addition. The instruction is this. The instruction itself is given here. I am actually talking about this instruction. What are the steps with respect to this particular instruction? Forget about any other instruction. I'm talking about only this instruction.
Sir, we need to add means we need to fetch R2 value into some
Right. We need to fetch the R2 value. So that means read the register R2. Next. Logically think about it. What you'll have to do?
again X value we need.
X is already there within the instruction.
Okay, okay.
X
Then
is
we
already
need to
there.
add.
Yes. So then you need to do add the immediate value, because when you brought the instruction, see why X you do not need to fetch. Fetch the instruction from memory location pointed by the program counter. Now this X is part of the instruction. X is not a register. X is an immediate value. So the value itself is there within the instruction. It's a 32-bit instruction. We are talking about a RISC instruction. RISC 32. Let's assume that 32. So some of those bits of the 32-bit instruction represent X. So you directly get the value of X. So next what you'll have to do? Add the immediate value X with R2. To generate the effective address of the memory read operation. That means X plus R2 will be performed. It will be stored temporarily, it will be stored somewhere. So, yeah. Now, next stage. What is the next stage?
Read X plus R2.
Yes. So read the content of the memory location pointed by X plus R2. So read the memory location pointed by X plus R2. Then last stage, last step, load the value received from memory into R1. So these are the 7 steps which are needed to accomplish the task. What was the task? Task was load R1, comma X R2. So anyone has a different opinion? Now, some of these steps can actually be combined to make some of the steps can be combined to make them as stage. If you carefully look into it, fetch the instruction from memory location pointed by the program counter and incrementing the program counter can be clubbed together. They can be done at the same time. Once the address is given to the memory for reading, you can immediately give the same address to a fixed hardware to increment the program counter. So that's why these two can be combined to make S1, stage 1. Decode the instruction to determine the operation to be performed. Now an instruction has a format. Some portion of the instruction determines that what are the operations, whereas the designated portion of the instruction, they actually hold the addresses of the registers. So these two are easily done in a single step, because decoding is trying to understand the meaning, whereas the field where the R2 is there, that field is not going to be used for decoding. It's an address of register. So these two actually can be combined. The third one is an arithmetic operation, because unless this S2 is completed, you cannot go to S3, because S3 performs what is the operation. S2 produces the data also, that R2. You require R2. You require X. That will come through S2. So here basically you do S3. The fourth one is a memory operation. This is separate, S4, and this is writing the result. You cannot do it at the same time unless the memory function is completed, you cannot write it back. So this one is S5. So with respect to this particular instruction, we can say that We divide the instruction now into stages. These are steps. Now these are stages. Stage S1, stage S2, stage S3, stage S4, stage 5. Now if you try to correlate with this one looks to be a stage like fetch. This one looks to be the stage called decode. This one looks to be the stage called execute. This one looks to be the stage called memory. This one looks to be the stage called write back. You'll have to understand these correlations. Not necessarily that all these stages are needed in each and every instruction. We are only talking about one instruction. Let us see that other instructions, and we'll see that whether we actually need separate stages or the same stages can be used for completing the job.
So can you repeat the names of the stages again?
These stages are fetch, decode, execute, memory, and write back. I think I already mentioned it on one of the earlier classes. So this is called fetch. This is called decode. This is called execute. This is called memory. This is called write back. FDEMW. Now, we may not require all these stages, particularly the advanced stages like EMW across all instructions. We'll see that where we do not require and where we require. But at least for this particular instruction, the instruction in hand, we require these stages. That we understood. Now let us see that how an arithmetic operation can be performed within the same framework. Is that clear up to this point? This logical grouping of these stages
Yes,
into logical grouping of the steps into stages, this must be clear in your mind. Okay. So I believe that you understood, all of you have understood that why there are 7 steps and how these steps can be logically grouped into stages like fetch, decode, execute, memory, and write back, particularly for this instruction. Now we shall explore that whether the same sequence can be used for executing other instruction. We have only seen one instruction load. We have many other instructions within the same RISC framework we are talking about. So now let's take example 2. Arithmetic and logic instructions. So in RISC architecture, the basic difference of the arithmetic and logic instructions with load, the difference, we need to understand the difference between load and ALU instructions. What can be identified here? First of all, there are either two registers or a source, two source registers, or a source register and an immediate value, as the operands. Whereas in case of load, we have seen that it was always one source register and one immediate value. Do you agree with me? In case of load, there was X, whereas in case of add, there is nothing like X, at least at present, whatever I am talking about. A typical ALU instruction where both the operands can be two registers, or one can be a register and an immediate value. So we can have instruction. I'll come to that point. And then the second one, the difference is, what is the second difference with respect to load? Can someone tell me?
Finally, three arguments, like two to add and one to store destination.
Yeah, in the previous one also there were three arguments. R1, X and R2. We have identified that the source arguments in this case are either two registers or one register and one immediate value, which was not the case in case of load. In case of load, it was always one register and one immediate value. What is the second difference? Another one difference. Think about the steps. Which step is
flag?
Which step may not be required? Which step may not be required, or may be required additionally? Go to the steps. The steps are very important to understand. Look into the steps. Let's think about that we are also doing the addition operation. So we need to do the addition operation also here. Maybe there the X will be replaced by another one register, R1 plus R2. But addition is required. But do you think that all other steps are required? I mean to say that this part is common. Up to the register reading, it's common. After that, do you think that all are needed? And if it is not needed, where is the change? For an instruction like this. So my instruction is now like this. Add R1, R2, R3, or add R1, R2, 100. These are the two instructions. Okay. So here two source register, here one source register and one immediate value. That's why we have understood the basic difference. In case of load, it was always like this, whereas in case of add, it can be like this or this.
Memory is not here.
Right. This is the point. So no memory access. No memory access is required. Because what it does R1 equals to R2 plus R3, or R1 equals to R2 plus 100. So this is the RTN for this, is the RTN for this. So where is the part of the memory? We do not need any memory operation here. Is that clear? The second point, the difference between load and ALU instruction, I'm talking about this ALU instruction. Okay. It does not require memory access. So now, if we write down the steps, if we agree with me, if you agree with me, we now need to write down the steps. Steps to complete the job. So fetch the instruction and increment the PC program counter. Second stage, decode the instruction and read the content source registers. Then third one, compute the sum. Fourth one, load the result.
So can you move the page to left?
Load the result into the destination register. These are the steps or stages. Now in between 3 and 4 there was another one stage, memory, so we do not need this. However, we are going for a generic design. We have decided that in the previous case we require 5 stages, 1 2 3 4 5. In this case we require 4, 1 2 3 4. So this is stage 1, this is stage 2, this is stage 3, this is stage 5. Where is stage 4? Stage 4 is not needed. So if I would like to design a circuit which can be used for both the instructions, load as well as this add instruction, I must introduce something new here. So that is what we are going to now understand, or let us generalize it more. The generalization says that, now generalization, of add as per the stages found in load. So the first one will be fetch, and increment the PC. Second one will be decode the instruction and read the operands. Just a minute. So decode the instructions and read the operands. Third is compute the arithmetic operation. Fourth stage is no action. That means we need to bypass the circuit here. That's why I need to write it no action. Because in my generic circuit, there will be something for memory reading. So I need to bypass it. That's why I need to mention it clearly that no action. Because while I design the circuit, I shall bypass this. There will be now multiplexers coming here because I need to bypass it. We'll see that how it can be done. And then finally load the result into the destination. So do you agree with me now with these 5 stages? Now this is fetch, this is decode, this is execute, this is memory, this is write back. FDEMW. So any other opinion? Anyone finding any difficulty in understanding this?
Sir,
Yes.
sir, this generalization is considering that we are doing it parallelly, like both the load and add together, or what?
No. These are not parallelly done. These are not parallelly. It's never parallelly done. We are talking about a uniprocessor, single processor. Okay. One instruction will be done, completed, then the other one will come. But the circuit that will be used to implement these instructions will be same. That's why it is generalization. There is nothing like parallelization up to this point I have talked about. All these instructions are executed sequentially, one after another, one after another. There is nothing like parallelism up to this point, even though there is a parallelism that we will come in the pipelining stage. But for time being, there is no parallelization. It's a sequential execution. One instruction goes out, then the other one comes like this. So here the circuit is same. The 5-stage circuit that you will be designing remains the same. It can be used for load, it can be used for add. That is what we are talking about. Clear?
Yes.
Okay. Anyone, any other doubt? Okay, so now let's go ahead with the example 3. It's a store instruction. Store, say R3, comma, X, R4. You know that the meaning of this. So the content of R3 goes to a memory location pointed by base address plus offset. Base address plus offset. Now, do you think that all 5 stages are required here? And if not required, which stage is not required? I want to understand. I want to get your opinion from you. Just logically think about the steps required to complete this instruction. Let me know which stage is not required for this instruction.
The fifth is not needed because the destination is not a register.
Right. Actually, 5th stage is not required because the write operation stops at the end of the 4th stage. That's it. 5th stage you do not need to do anything because the destination is memory, which is already, it's a write operation which is already done in the 4th stage, memory operation. So correct. So what we can write, the first stage is fetch the instruction and increment the program counter. Second one is decode the instruction and read R4 and R3. Compute the effective address R4 plus X store the content you see why we have read here R3 at this stage. Now you understand that why we are reading the value of R3 here, because we need this. That's why in the decode stage we are not only reading R4, we are also reading R3. We are not using this at this stage, but we need to read it, get the value out of the register file, store it somewhere in temporary location. So store the content of R3 into memory location. Pointed by X plus R4. 5th stage is no action. So this is write back, this is memory, this is execute, this is decode, this is fetch. So FDEMW, same FDEMW, FDEMW. Earlier also you have seen that FDEMW, the same stages. So all these 3 instructions which actually cover probably the 80% of the instructions, because it's a load store architecture. Loading something from memory, use load. Storing something into memory, use store. Any arithmetic operation, use this. So more than 90% of the instructions will fall into this category. So from here, if we'd like to generalize these operations, what we can do? We can say step 1 action, fetch an instruction and increment the program counter. Step 2, decode the instruction and read register from the register file. Step 3, perform an ALU operation if needed. I will also tell you that where the ALU operation is not needed. Fourth one is read or write memory data if the instruction involves a memory operation. Fifth one is write the result into display. Now let us look into another instruction which is also very common, and let us see that what are the operations. Example 4. Move. This is also very common instruction. Move R1, R2. Moving the content of a register into another register. Fetch the instruction and increment PC. Decode the instruction and read R2. 3. Third stage. What will be the third stage here?
Not required.
Yes, so no action. Fourth stage. So no action. Fifth stage. Write the value of R2 into R1. So again the same framework: fetch, decode, execute, memory, write back. Here these two stages are not needed. So we have seen that there are 5 stages. Fetch, decode, execute. This is F, this is decode, this is execute, this is memory, this is write back. What we can say, this is mandatory, this is mandatory, this may be required, may not be required, this may be required, may not be required, this may be required, may not be required. For some instruction, we require 5. For some instructions, so if I basically write down the categories, it will be something like that: F, D, E, M, W. We may also have F, D, blank, blank, W. We may have F, D, E, blank, W. We may have F, D, E, M, blank. This is load type. This is move type. This is ALU type. This is store type. Is that clear? This encoding? Anyone? Any doubt up to this point? So in all these instructions, other than memory read write or arithmetic operation, what is the most common operation here? Can someone tell me what kind of common operation being done, so that we first understand that how that kind of circuit can be designed?
Fetch and decode.
No, I'm not talking about stages. I'm talking about a common unit of operation. Okay. Irrespective of except memory read write and arithmetic operation, there is one circuit which is very much important. I'm talking about a particular circuit that is very important to implement many of these things. What is that circuit?
Decoder.
Decoder is obviously it's a combinational circuit which we require it. I'm talking about, you see, the flow of data, how that flow of data happens across multiple instructions. You will find that there is a very common characteristics that's called data transfer from one register to other register. Often you will find all these operations require transfer of data from one location to the other location. That's a very common circuit required. So we call it register transfer. So transferring the value from one register to other register is very common in many of these operations. Even when you are transferring something from processor to the memory, if you can assume that memory is also a register, that is also a register transfer. So transferring data from one location to other location is very important, and that is the primary building block of any sequential circuit, particularly the CPU. Transferring data, because the control unit design, I know that it's a complex part, but that's one unit. You design one control unit, that's fine. But data transfer units are required at various stages. At various stages, you require data transfer units. From here to there, from here to there, you require at many places. You read from a register, put it into a temporary register. That's a register requirement. You give the value from the register to the arithmetic logic unit, and immediately after arithmetic logic unit, the value goes to another register. So essentially, it's a data transfer from a register to register. In between, there is a fixed circuit. That's a combinational circuit that does arithmetic logic operation. Similarly, when the result is computed, it is stored in a temporary register. From there, you need to write it back to the register file. That's another. So more or less, you require to implement transfer of data from one location to other location. Here, majority of these locations are registers. Some registers are known registers like R1, R2, R3, R4 that we can access it. You also require temporary registers within the processor which are not accessible by the programmer, but as a designer you need to include them. Those are not directly accessible through programming, but they are needed to perform the task. That's why register transfer is the most important component inside the processor other than the control unit. Control unit is something unique. We cannot compromise on it. Arithmetic logic unit, you probably know it because you have already done digital circuits. You know that how to design adders, how to design subtractor, how to design multiplier, possibly. But transfer of value from one location to the other location, that is a primary unit and which we need to understand. That's why probably if you remember in the first lab class itself, when I told you, you carefully look into this circuit, how to perform data transfer efficiently from one register to other register. That is what we require. Okay, so register transfer is extremely important. Not only designing the register, but how to transfer the value from one register to another register, designated register. It's not like that you will be sending to only one register. Your registers may be at a different location. So selecting the register is very important. That's why the register transfer is very important. When we are talking about data transfer from one register to another register, there are things like you need to select the register, source register, you need to select the destination register. So I shall not advance the course because today I will finish it by 10:30. I'll have to go somewhere. But from this point onwards, since we will be directly going into the designing of the circuit, your job is to recap these portions as well as recap the knowledge on parallel in, parallel out registers. Mostly we will be considering parallel in, parallel out registers. It's not a serially, the input is going serially into the register. There are 32 bits in a register because it's a RISC-32 architecture. All 32 lines will go in parallel and they will come out in parallel. There is no concept of serial at this point of time. Okay. So what I want you to learn the basic understanding of a 32-bit parallel in, parallel out register and see that how these registers are implemented in Logisim, because we require the Logisim circuit a lot for designing. So your 90% of focus must be now to see that how these registers can be used. Other combinational circuits like designing multiplexer, decoders, you all know it. You just need to recap those circuits. Okay. But this register transfer is very important. The clocking of the cycles, how, what is the positive age and negative age, how much time it is taking, that is very important. I know that one component within the processor which is complex, that's a control unit. That's why it's a separate thing. Control unit designing is completely separate thing. We shall look into it at later stage. At this stage, we are not going for control unit designing because that's a little bit complex. But the easier part is data transfer. So let us now see that how data transfer can be implemented properly. So the register file implementation, how a block of registers. We are not dealing with two registers. We are dealing with maybe 32 registers in register files, as well as there are temporary registers in between stages. In between stages, there will be temporary registers. So we need to access all these registers through hardware circuits, and we need to transfer data from one register to other register. That's why the concept of register file designing as well as register transfer is very important. And you must practice this in Logisim. The blocks are already there in the Logisim circuit. You look into those things, look into the help file, look into various ports of those registers, parallel in, parallel out. I'm just asking you to look into the parallel in, parallel out registers. At present, we need that. No serialing, nothing. Okay.
Okay, sir.
So any doubt up to this point? Next class, I shall start the designing of register file and register transfer circuit, and also we need to implement it in the next lab. So Friday lab, we are going to implement it. But before that, you must recap your Logisim knowledge on that. That's very important. The assignments are going to be on the circuit designing now, particularly initial stages only register file. So that's it. If there is any question, you can ask me. Otherwise, I'll stop here. Good. If there is no question, thank you. Thank you all. I'm closing the call.
Thank you.